We're going to consider now diffraction. We have diffraction when we have an obstacle between the transmitting and the receiving antenna. Now, for most situations that it's difficult to model, but there are some very simple cases that actually allow some mathematical formulation, and one of them is what is known as knife edge diffraction. In that case, we assume that we have a transmitting and a receiving antenna, and in the middle we have certain obstacle that actually its width is very small in terms of the wavelength, and this is why we call this like a knife edge, like the edge of a knife. In that case, although the line of sight between the transmitting and antenna is blocked, it is possible to have a transmission between both antennas, and the responsible for that is what is known as diffraction. If you want the physical explanation, is that we have an illuminating wave on that edge, and then there is a secondary wave that is generated here because of the interaction between that obstacle and the incident wave, and that secondary radiation is received by the antenna. In the model we are going to use, we have our two antennas. dt is the distance from the transmitter to the edge, dr from the receiver to the edge, and h is the distance, is the clearance from line of sight to the top of the obstacle. And notice that h is going to be positive when we are blocking the line of sight between the two antennas. Well, for that particular geometry, we can compute that parameter v. Actually, notice that it depends on the value of h, and remember, h positive means that line of sight is blocked, depends on dt and dr, and also depends on the wavelength. And for that, it is possible to obtain the field relative to free space depending on the value of that parameter v. So, if h is positive, line of sight is blocking, b is positive, so this area here is, if you want, the shadow region. And if v is negative, that means that we are above here, so we are in the lead region. So notice that in this area, essentially, we are around 0 dBs. That means that the field relative to free space is essentially the same. While down here, although we have attenuation, 20, 15, 10 dBs, it's still possible to have signal reception, although the line of sight between the two antennas is blocked. Now, let's look a little more with a little bit more detail what is going on. So these are some simulations in which we are plotting in that color scale the losses compared to free space. We have our edge obstacle here, and we are assuming that our transmitting antenna it's at the same height, has the same height of the knife edge, and we're considering three different frequencies: 100 MHz, 1 GHz, and 10 GHz. So notice that if we are here in this region here, which is in the shadow region, we still have certain, we have some losses, but we are still able to receive something. If we increase the frequency, and as we increase the frequency, you can see that, considering the same geometry, we are moving towards that blue region, and notice that the blue means that the losses are higher. So one of the effects of diffraction is that as the frequency increases, those diffraction losses are higher. So if we plot it now in this graph, here we have the field relative to free space. We have the difference between the receiver and the obstacle, and for instance we can see that for a given place, let's see that's 15 meters, so that means that the height of our obstacle is 15 meters below the obstacle. We can see that as a function of the frequency, every time I multiply the frequency by a factor of 10, those losses reduce by a factor of 10. So actually the attenuation in the shadow region is proportional to the frequency. And one important thing also to realize is that for 0 meters, that is, the receiver is at the same height as the obstacle, we always lose 6 dBs, no matter the frequency. We can see this in more detail here. in which I'm playing with the position of the transmitter. Here I have the transmitter at 15 meters, at 20 meters, or at 35 meters. Our edge always has a height of 20 meters, and the frequency is always the same, 1 gigahertz. And you can see that in this line here, if I have my receive antenna here in this line, or in this line, or in this line, I always lose 6 dBs. So here comes an interesting question. Now, well, apparently my line of sight between transmitter and receiver is not obstructed, but still I'm losing 6 dBs. So when can I consider that a certain obstacle is not interfering with my propagation path, and I can assume that I have free space propagation condition? Well, the answer is given by something that is known as the Fresnel ellipsoid. Now, the definition of the Fresnel ellipsoid is the following. Imagine that we have a transmitting and a receiving antenna. So I have a direct path, which is D1 plus D2, and then I can imagine another path that travels that distance and this distance here. Okay? Well, when that distance has a difference, which is D1 plus D2 plus n times have a wavelength, that defines an ellipsoid, which is called the Fresnel ellipsoid. When that difference is only have a wavelength, this is the first Fresnel ellipsoid, and then I can define the nth Fresnel ellipsoid according to this value n. Well, I can find the radius of the Fresnel ellipsoid depending on the position of D1, D2 given by those expressions. Notice that the first Fresnel ellipsoid defines a certain volume of space. Well, then the criterion is the following. If within the volume defined by the radius of the first Fresnel ellipsoid there is not any obstacle, then there are no diffraction losses, and we consider line of sight conditions. So actually the Fresnel ellipsoid is the criteria we will use to decide if we are in free space propagation conditions or we have to consider diffractions. Now, for more complex situations like this one, in which we are assuming that well, we have a certain skyline and we are assuming that we have a transmitting antenna here, maybe a FM transmitter at 108 megahertz, well, we can model, using that naive edge diffraction, we can see how it's possible to have certain signal received, although we have these blocking buildings due to the diffraction. And we can see also how multiple diffraction can occur. For instance, the diffraction caused in this building actually then is diffracted by this building, and that gives the overall reception. Numerical analysis can be extended to complex situations. Imagine this. This is a city in which we are plotting an antenna here, and we are computing the propagation losses. In that case, we have the effect of reflection of the ground, so this is why we have this sort of maxima and minima due to ground reflection. We can see here how we have diffraction caused in those edges. We can see how we have reflection of the buildings that are able to give certain coverage. So notice that with the tools we have already presented, essentially considering reflections, diffraction, it is possible to include this in numerical analysis and being able to make predictions of propagation in certain environments. So to end this blog, just to mention that diffraction is caused by obstacles that block the line of sight between transmitting and receiving antenna that will cause an attenuation. And the second important issue is, well, how we determine if diffraction is occurring, and for that we have to use the first Fresnel ellipsoid to decide if the line, and as long as the first Fresnel ellipsoid is clear of obstacle, we can assume free space propagation conditions.